All right, the unit circle. So the unit circle is basically a memory device. It's something that we use to remember all the values of trig ratios that we'll need to know by heart at any point in our math career. If it's not on the unit circle, it's not a trig value you're expected to remember. So it's basically a memory device. It takes all these values that you're supposed to know and places them in like a visual representation, so it's a lot easier to remember them. So in order to see how this works, we're going to build it from the ground up. And the first thing we need to know is what a unit circle is in the first place. A unit circle is a circle whose center is at the origin and whose radius is 1. That radius being 1 is going to be important a little bit later on, and you'll see why. So when you have an angle in standard position, in the unit circle. So unit circle, standard position, terminal side on the x-axis. And then that's my initial side, sorry. My terminal side, we're going to say it lands somewhere in the first quadrant. Now, if I were to drop a perpendicular, you know, I've done that several times up to this point, to make a right triangle, then if I were to label the point where the terminal side intersects the circle as x comma y, some interesting things start to happen in this triangle. So you can see, first of all, that I know the legs of the triangle, because to get to the point xy, I would go over x and up y. And then I know the hypotenuse of this triangle because it is also a radius of the circle. So the hypotenuse of this triangle is 1. So if I go to set up sine and cosine ratios from this right triangle, and I say the cosine of theta, by the way, that's the Greek letter theta, often used to represent an angle, is adjacent over hypotenuse. So that means that x is the same thing as the cosine of the angle. If I set up sine, it's opposite over hypotenuse. That means that y is the sine of the angle. So that means if I look at any coordinate of any point on this circle, and I think about the angle whose terminal side crosses through that point, the coordinates of that point are cosine of that angle and sine of that angle. So when we deal in the unit circle, it's always 1. Now, circle, we're only going to care about angles whose reference angles are either coming from special right triangles or quadrantal angles. So if you think about the two types of special right triangles we have, 45, 45, 90, and 30, 60, 90, 30 degree, 45 degree, and 60 degree angles are reference angles that we could care about because those come from the special right triangles. And quadrantal angles are angles whose terminal side land on either the x or the y-axis. So that could be a reference angle of 0 degrees if it lands on the x, or 90 degrees if it lands on the y. So when we're looking at this unit circle, we're only going to care about angles whose reference angles are 0, 30, 45, 60, and 90. So those are going to tell us the angles we care about in the unit circle. So let's start in quadrant 1. Quadrant 1, my 0 degree reference angle is just going to happen at 0 degrees, as if I haven't even opened up my terminal side. My next side would land at 30 because that's the smallest of these reference angles that I care about. My next one will be 45, next one will be 60, last one will be 90. And again, that's because those come from special right triangles or they land on quadrantal angles. Now when I look at quadrant 2, this is again 90, it's still marked from standard position. If I looked at the next angle, this would be a 60 degree reference angle, which means basically this angle is 120 degrees. It's 180 minus 60. So the next one will be 180 minus 45, which is 135, 180 minus 30, which is 150, and then 180. Now if I look at quadrant, by doing the angle at 120 degrees. So let's say I took 180, 120, and I wanted to convert it to radians. So degrees on bottom, radians on top. There are 180 degrees in pi radians. Now when you convert this to radians, you're going to leave the pi in your answer. And really all you have to simplify is 120 over 180. Both of those are divisible by 60, so 2/3, so 2 pi over 3. Okay, I'm going to draw two 30, 60, 90 triangles. So here's 1, 60, 30, 90, and I'm gonna draw another one here. Those are intended to be sort of the same size, but my drawing skills are poor today. Let's just make that a little straighter. Now we know we learned the ratios of the sides in a special right triangle with 30, 60, 90. That side opposite 30 is x, side opposite the right angle is 2x, and the side opposite 60 is x root 3. Now if I look at the right-hand triangle and think of it as a triangle in the unit circle, remember the hypotenuse of a triangle in the unit. So if I label that 1, if these two triangles are going to represent the same thing, 2x would have to equal 1, which means my x value is 1/2, which tells me that my side opposite the 30 in the unit circle triangle is going to be 1/2. And the side opposite 60 in the unit circle triangle is going to be 1/2 square root 3, which is the same thing as square root 3 over 2. So now if I go to find my cosine of 30 degrees, that would be adjacent over hypotenuse, which is root 3 over 2, divided by 1, which is root 3 over 2. And the sine of 30 degrees is 1/2 over 1, opposite of hypotenuse, which is 1/2. So that means on my unit this time use the 60-degree angle. The cosine of 60 is adjacent over hypotenuse, that's 1/2 over 1, which is 1/2. And the sine of 60 is opposite over hypotenuse, which is root 3 over 2 over 1, which is root 3 over 2. So my units, my reference angles are like 180 plus, my angles are like reference angles plus the 180. So 180 plus 30, 180 plus 45, 180 plus 60, and then this is 270. And then in my fourth quadrant, it's 270 degrees, and then you can think of 360, because I've gone all the way around, 360 minus 30, 360 minus 45, and 360 minus 60. So these are going to be the degree measures that I'm going to put on my unit circle. So I'm going to go to and that would be circle thing, but units 45, 45, 90 triangle. So I'm going to draw two versions of that triangle. One of them is going to be my unit circle triangle. One of them is going to be my generic one. So in the generic one, the legs are both x, and the hypotenuse is x root 2. Now unit circle one, the hypotenuse is 1. So the hypotenuses should be the same length. So that tells me that x is 1 divided by the square root of 2, which is root 2 over 2. So that means the length of each of my legs is root 2 over 2. So the sine of 45 would be opposite of hypotenuse, root 2 over 2 over 1, which is root 2 over 2. And the cosine would be root 2 over 2 over 1 as well. And do the same at 60, similar with the circle page. I'm going to write that all my points in the unit circle are cosine of theta, comma, sine of theta. All right. So those are going to be the points around the outside of the circle. We'll talk more about those in a minute. And I'm going to fill in those degree measures. So there are all those measures in degrees. You can pause the video and copy those down if you want. Now, when we measure angles, we can measure them in degrees, or we can measure them in radians. So what I'm going to do is take all of these angle values that are on my unit circle that are in degrees, and I'm going to convert each of them into radians. So I'm going to show you an example of that. My radian value at 120. Now I can go ahead and do the same sort of conversion with all of these. I would encourage you to do it with a couple of them, just get the practice in the conversion. But you can also pause the video to do that. And when you unpause it, I will have filled in all the radian measures that I've converted. All right, so there are all the converted radian values. If you want to pause, oops, I left off pi over 2, so let me fix that. If you want to pause the video and write those down, you certainly can. But I want to point out a few patterns. Now again, this year we're not going to memorize the unit circle. We're just going to use it, know how to use it when it's in front of us. But I want to point out some patterns that when you go to memorize it next year, that makes this so useful. So first of all, I want you to look at all the angles whose reference angle is 30. So that would be here at 30 degrees, here at 150, here at 210, and here at 330. And I want you to look at the radian measures. Pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. All of the 30-degree reference angles have a denominator of 6 when you look at the radian values. If you look at the 45-degree reference angles, they all have denominators of 4. And if you look at the 60-degree ones, they all have denominators of 3. So that's one pattern that we can look at to memorize the radian values. Look at the numerators in each of the quadrants now. In first quadrant, the numerator is all pi. In second quadrant, the numerator is all 1 less than the denominator, which makes sense. It's pi minus one of those things. In the third quadrant, it's always 1 bigger than the denominator. Again, pi plus one of those things. And then in the fourth quadrant, it's 1 less than twice the denominator. So like 2 pi minus one of those things. So that's a way of remembering the radian values on there. And again, if we didn't have this circle, it would be really hard to see those patterns. Now, for the points around the outside, in order to understand that, we're going to look at a couple of special right triangles. So remember, the x value of the point was cosine and the y value was sine. So my x value then, at the point where the angle is 30, would be root 3 over 2, and my y value would be 1/2. Now if I go to be the flip of the ones at 30, which kind of makes sense, right? Because then you're using the same right triangle for those two things. Now I'm going to do something. Coordinates at 45 are going to be root 2 over 2 for both the x and the y. Now, that is as far as we need to go with the right triangles. The rest of the unit circle is going to fill itself out beautifully. So watch this. This is a unit circle, right? The radius of the unit circle is 1. So if I look at the coordinates at angle 0, I have moved over 1 because the radius is 1 and up nothing. So that means basically the cosine of 0 degrees is 1, and you can check that on your calculator. And the sine of 0 degrees is 0. Look at the 90-degree angle. Again, radius is 1, that's 0, 1. The cosine of 90 is 0, the sine of 90 is 1. And that works for pi, this is -1, 0, and 3 pi over 2, this is 0, -1. Now, to fill in the rest of the unit circle, I want you to understand we're using the 30, 60, 90, and the 45, 45, 90 triangle to fill them in, right? So all of the values around should be the same with one little difference. If I were to look at the coordinate at 60 degrees and the coordinate at 120, you see that those are the same height, so they're going to have the same y value, and that they're the same distance from the y-axis, so the x value is going to be the same, but instead of it being 1/2, we've moved into the second quadrant. It's -1/2. So the cosine of 120 is going to be -1/2, and the sine of 120 is going to be root 3 over 2. In fact, I could say the same thing for all the things in the second quadrant. They're going to have the same coordinates as the angle that has their same reference angle. So 135 would have the same coordinates as 45, except its x coordinate is going to be negative. 150 would have the same as 30, except the x would be negative. Now, if I look in the third quadrant, the same idea happens, except you're in the third quadrant. So both the x and the y are negative. So this is negative root 3 over 2 and -1/2 because it matches up with the 30-degree reference angle. This is negative root 2 over 2 and negative root 2 over 2 because it matches up with the 45-degree reference angle. And this is -1/2, negative root 3 over 2, because it matches up with the 60-degree reference angle. So in the fourth quadrant, it's the x that's positive and the y that's negative, because it operates just like regular points. So then this is going to be 1/2, negative root 3 over 2, root 2 over 2, negative root 2 over 2, and root 3 over 2, -1/2. Now, my unit circle is now filled out. So I want to point something out about the values that go around the unit circle. And again, make it sort of a thing that makes it easy to understand and to use as a memory tool. So if you look at the numbers around the edge, there's 0, 1/2, root 2 over 2, root 3 over 2, and 1. So if you think about that as being square root of something over 2, that basically cycles up through 0, 1, 2, 3, 4. Square root of 0 over 2, 0. Square root of 1 over 2, 1/2. Square root of 2 over 2, square root of 3 over 2, square root of 4 over 2, which is 1. And then if you look at the values of cosine, they start at 1 and go down to 0, and then down to -1, back to 0, and then back to 1. And if you look at the values of sine, they do the same thing, except they start at 0, go up to 1, come back to 0, go down to -1, and come back to 0. So putting all these things on the unit circle not only gives us sort of like an easy way of remembering when things are positive and negative because they land in the correct quadrants, they also give us a nice way of actually arranging the values on the circle so we can put them in the right spot. Now, I'm gonna stop this video here. Actually, no, I'm gonna go ahead and do the last few problems and then we'll be done with this. So let me erase here and show you how to use the unit circle. I'm gonna do a few examples so you can see how this works. So let's start by saying I wanted to find the sine of 240 degrees. So the first thing you need to understand is that I want a y value because on the unit circle, sine is the y value. By the way, cosine and sine, they go in alphabetical order. Cosine's the x, sine's the y. So I would want to find my angle of 240 degrees, which is right here, and I want the y value there, which is -root 3 over 2. And that is the sine of 240. Now, if I wanted to find the cosine of, say, 2 pi over 3, cosine's the next value. Notice this is in radians, not degrees, so I need to find 2 pi over 3 radians and get the x value, -1/2. Now, if I gave you something like cosine of -150 degrees, -150 doesn't appear in my unit circle, but remember what -150 means. It means we start at the x-axis, but instead of rising, we go down. So we would go down 90 degrees, and then another 60 to get to 150. That's going to land at 210. And again, cosine is the x value, so I want the x value at that point, which is -root 3 over 2. If I gave you something like the sine of 11 pi over 3, 11 pi over 3 is also not on the unit circle, but it is coterminal with something on the unit circle. If I were to take the 11 pi over 3 and take away 2 pi, which is a full rotation, that's the same thing as 6 pi over 3, I would get 5 pi over 3, which is right there, and because it's sine, I want the y value, which is -root 3 over 2. So you can tell, you just need to know whether you're working with the x value or the y value, and you need to know how to find your angle on the unit circle. And if your angle isn't coterminal with something on the unit circle, you're not going to be expected to know the trig value of that thing in your head. Now, a couple of problems that are a little bit different. If I find the inverse sine of -root 3 over 2, what that's asking is I want all the angles whose sine is -root 3 over 2. So that means on the unit circle, I would want to look, remember sine is the y value, I would want to find the points whose y value is -root 3 over 2 and give the angles back. So in this case, let's answer in degrees. So -root 3 over 2 occurs as the y value in 240 and at 300 degrees. If I were to do, say, the inverse cosine of -1, let's say this time ask for it in radians. Cosine is the y value, cosine is the x value, so I would want an angle who gives me angular angles whose x value is -1. Well, there's only one of those on the unit circle. It happens at pi. Now, the last two examples are using trig functions that we've talked about before. The first one is secant. Remember that secant, let's say I wanted to find the secant of 60 degrees. Remember that secant is 1 over cosine. So cosine is the x value in the unit circle. So I would go to 60 degrees. I get the x value, that's 1 over 2. And secant is the flip of that. So I would take the 1 over 2 and flip it to 2 over 1, which is 2. Cosecant would be the flip of sine. So if I asked you to find the cosecant, you would actually find the y value and flip it. Now, last example, tangent. Tangent and cotangent are a little strange because they're not on the unit circle, and they're not just flips of things in the unit circle like secant and cosecant are. So to understand tangent, I want to point something out really quickly. Sine is opposite over hypotenuse, right? Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Well, if I were to take sine and divide it by cosine, that's like saying opposite over hypotenuse divided by adjacent over hypotenuse. If I did same switch flip, it's opposite over hypotenuse times hypotenuse over adjacent. The hypotenuses cancel, that's opposite over adjacent, which is tangent. So if I want to find tangent on stuff from the unit circle, tangent of an angle is sine of that angle divided by the cosine of that angle. Likewise, cotangent would be the flip of that, cosine of that angle divided by the sine of that angle. So for this problem down here, tangent of 5 pi over 6, I would say it's sine of 5 pi over 6 divided by the cosine of 5 pi over 6, which means I would find 5 pi over 6 on the unit circle, right here. Sine is the y value, that's 1/2. Cosine is the x value, so that's negative root 3 over 2. And I'm running out of room. But if I do same switch flip, that would be 1/2 times negative 2 over root 3, which is negative 1 over root 3. And we don't want to leave a square root in the bottom, so it would be negative square root 3 over 3. So if you're finding secant or cosecant, you find the appropriate cosine or sine and flip it. If you're trying to find tangent or cotangent, tangent is sine over cosine, cotangent is cosine over sine.